scientists have recorded one of the clearest gravitational wave signals ever detected, known as GW250114, captured on January 14, 2025. The signal came from two black holes merging and was unusually sharp, allowing researchers to measure multiple ringdown tones from the newly formed black hole. This gave physicists a rare chance to test Einstein's general relativity with exceptional precision. And once again, the results match the theory's predictions. In this video, we will explore what GW250114 revealed, why it matters, and what comes next. Let's get started. GW250114 was detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, part of the international network of instruments designed to measure tiny ripples in spacetime. The signal arrived on January 14, 2025, produced by two black holes spiraling inward and merging somewhere far beyond our galaxy. Black hole mergers have become a familiar part of gravitational wave astronomy since the first historic detection in 2015. But GW250114 immediately attracted attention because of how clearly it was recorded. The waveform stood out with exceptional strength, giving scientists one of the cleanest observations of a merger ever captured. That clarity mattered most in the final stage of the event. After two black holes collide, the newly formed black hole does not settle instantly. Instead, it enters what physicists call the ringdown phase, where it briefly vibrates as it stabilizes. This vibration produces gravitational waves at specific frequencies, often described as tones. Each tone fades over time, but together they form a kind of fingerprint of the black hole that remains after the merger. In most detections, only the strongest tone can be measured with confidence. GW250114 was different. Researchers were able to identify two distinct tones clearly, and even place meaningful limits on a third. This is a major step because multiple tones provide much more information than a single one. These measurements allow scientists to determine the final black hole's mass and spin with greater precision, and they also make it possible to perform deeper tests of gravity itself. In other words, GW250114 was not just another signal confirming that black holes merge. It was an unusually detailed event that gave researchers a rare opportunity to study the behavior of spacetime under extreme conditions. This is what makes it one of the most important gravitational wave detections of the past decade. Not because the merger was unique, but because the universe delivered it with enough clarity to reveal new layers of detail. The real scientific value of GW250114 lies in what those ringdown tones allow physicists to test. Einstein's theory of general relativity predicts that black holes are remarkably simple objects. Once a black hole forms, it should be fully described by only a few properties, mainly its mass and spin. This idea is central to classical black hole physics. No matter how complicated the merger is, the final black hole should settle into a predictable form. The ringdown phase provides one of the cleanest ways to check this. Each tone emitted during ringdown depends directly on the same underlying black hole properties. That means researchers can use the tones as independent measurements of the same object. If general relativity is correct, every measured tone should point back to the same mass and spin combination. If the tones disagree, that could indicate that something about gravity behaves differently than Einstein predicted. For GW250114, the tones aligned perfectly. The black hole's inferred properties were consistent across the measurements, matching general relativity with extraordinary precision. This makes GW250114 one of the strongest observational tests of Einstein's theory in the extreme gravity regime. The event also connects to another major prediction in black hole science. Hawking's area theorem, which states that the total surface area of black hole horizons cannot decrease in any physical process. In mergers, the final black hole should always have a larger horizon area than the two original black holes combined. Analyses of GW 250114 were consistent with this expectation as well, adding another layer of confirmation to the classical picture of black hole behavior. That is why detections like GW 250114 matter so much. They sharpen the boundaries of what we know. Every time general relativity survives a stronger test, the space where new physics could appear becomes narrower and more clearly defined. The wave signal, GW 250114, represents a turning point in what gravitational wave science can do. In the earliest years, the major breakthrough was simply proving that gravitational waves could be detected at all. Now, the field is moving into an era where signals are detailed enough to probe black holes with increasing precision. Measuring multiple ringdown tones is part of what researchers call black hole spectroscopy. Studying black holes through their vibrational signatures, much like scientists study atoms through spectral lines. As detectors improve, these measurements will become more common. Future gravitational wave observatories are expected to record mergers with even greater clarity, allowing scientists to extract more tones, test gravity more rigorously, and explore black hole physics in deeper detail. Next-generation ground-based detectors, such as the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will dramatically expand the number of detectable events and the precision of their measurements. Meanwhile, the planned space-based mission, LISA, expected in the 2030s, will open an entirely new window by observing gravitational waves from much larger black holes and different kinds of cosmic systems. With these tools, physicists hope to answer questions that remain open. Are black holes exactly as general relativity describes them? Could subtle deviations appear in extreme conditions? Do gravitational waves carry hints of physics beyond Einstein? And ultimately, where does our current understanding of gravity break down? GW 250114 does not provide those answers yet, but it shows the path forward. It demonstrates that gravitational wave detectors are becoming precise enough to test fundamental laws in ways that were impossible only a decade ago. For now, Einstein's theory continues to hold, but the long-term goal of physics is not simply repeated confirmation. The goal is to push our theories until we find the edges, because that is where deeper truths about the universe are revealed. The wave signal, GW 250114, is one of the clearest gravitational wave signals ever recorded, offering a rare precision test of Einstein's gravity. Once again, general relativity holds strong, but the search for its limits continues. With future detectors, events like this may eventually reveal what lies beyond Einstein's theory.